The greatest mathematical invention or discovery in the 1600s was integral calculus. This tool not only allowed the solution of many unsolvable problems, but also made quick work of many laborious processes in math. Hi, my name is Jason Rosenberry, and in today's lesson we will be investigating the definite integral. In this section we move from finite sums to infinite sums and look at some applications. Let's start by setting up some notation. Sigma notation. The Greek capital letter sigma stands for sum. The index k tells us where to begin the sum, the number below the sigma, and where to end the sum, the number above the sigma. If the infinity symbol appears above the sigma symbol, it indicates that the terms go on indefinitely. We use sigma notation to write the sum of the area of an infinite number of rectangles between the graph of a curve and the x-axis. Let's take a look at that. Definition: the definite integral as a limit of Riemann sums. Let f be a function defined on a closed interval from a to b for any partition P of a to b, the closed interval a to b. Let the numbers c sub k be chosen arbitrarily in the subintervals x sub k minus 1 to x sub k. If there exists a number I such that the limit as p goes to 0, this is actually the norm of partition P, which I'll explain in a moment. The limit as the norm of partition P goes to 0 of the sum as k goes from 1 to n, f of c sub k delta x sub k equals I, no matter how p and the c sub k's are chosen. Then f is integrable on the closed interval from a to b, and I is the definite integral of f over that interval from a to b. That was quite a mouthful. Let's take a look at a graphical representation of what we just covered. This sum right here, this sum, which depends on the partition P and the choice of the numbers c sub k, is a Riemann sum for function f on the interval from a to b. Now compare both pictures with one another. As the partitions of the closed interval from a to b become finer and finer, meaning we're allowing the width of our rectangles to get smaller and smaller and smaller, we would expect the rectangles defined by the partitions to approximate the region between the x-axis and the graph of f with increasing accuracy. Just as we covered in a previous section, rectangle approximations using either left endpoints, right endpoints, or midpoints always converge to a common value in the limit. All Riemann sums for a given function on a to b converge to a common value as long as the lengths of the subintervals, or width of rectangles, all tend to 0. So by writing this right here, the norm of partition P approaching 0 means we will take the largest partition that we have and make sure that one approaches 0, which means or implies that all smaller partitions will also go to 0 as well. So the limit of that sum will approach some finite number, which we call I, and that would be the area under the curve from a to b. I want to also point out that notice that sometimes area is below the x-axis, sometimes area is above the x-axis. When we compute this area from left to right, it's a cumulative area, meaning area below the x-axis will cancel out area that's above the x-axis. So again, it is possible at the end of one of our problems to end up with a negative answer, simply meaning that there was more area under the x-axis than above the x-axis. Another conclusion to make about a continuous function is made in the following theorem. Theorem 1. The existence of definite integrals. All continuous functions are integrable. That is, if a function f is continuous on a closed interval from a to b, then its definite integral over the same closed interval from a to b exists. This is read the integral from a to b of f of x dx. When you find the value of the integral, you have evaluated the integral. The lower limit of integration is a, so if our interval is, our partition goes from, or closed interval goes from a to b, a is the lower limit of integration, b is the upper limit of integration. Here's the function that's involved and with respect to which variable. Let's work with this notation. Express the limit as a definite integral. Number one, we want the limit as n approaches infinity of the sum as k goes from 1 to n of c sub k squared delta x from 0 to 2. So one possible answer would be, this would be the same thing as the definite integral from 0 to 2 of our function. Now the expression has a c sub k squared. We can call that x squared, but since I've chosen the variable x, we now must say dx. Number two, limit as n approaches infinity of the sum k goes from 1 to n of the square root of 4 minus c sub k squared delta x from 0 to 1. We would write that as the definite integral from 0 to 1. What is the function? The function is the square root of 4 minus, I'm going to use just a different variable this time, maybe y squared, but now we must say dy. We have approximated the area between a function and the x-axis with a finite sum. Now we can do that with an infinite sum, which is an integral. Definition: area under a curve as a definite integral. If y equals f of x is non-negative and integrable over a closed interval from a to b, then the area under the curve y equals f of x from a to b is the integral of f from a to b and is notated as the following. So the area A is equal to the definite integral from a to b of f of x dx. Let's try an example. Use the graph of the integrand, which is this part right here. Use the graph of the integrand and areas to evaluate the integral. So what this problem is asking us to find is the area under this curve from -3 to 3. So let's take a look at the graph of square root of 9 minus x squared. So here's the graph of our function square root of 9 minus x squared, and we're being asked to find the area under this curve from -3 to +3. We can do so by using some geometric formulas. Since this is a circle, semicircle, we know that the area is equal to 1/2 pi r squared. So area is equal to 1/2 pi r squared. So with our case, our area A would equal 1/2 times pi times the radius of this circle would be 3 units. So the area in question would be 1/2 times pi times 3 squared, which is 9/2 pi. Therefore, we can write the definite integral from -3 to +3 of square root 9 minus x squared dx is equal to 9/2 pi. Let's try another. Use the graph of the integrand and areas to evaluate the integral. Our definite integral is from -1 to 1, 2 minus the absolute value of x dx. So again, let's first take a look at the graph of 2 minus absolute value of x. So here's the graph of our function 2 minus absolute value of x, and we want to find the area from x equals -1 to x equals +1 under this function. So we're finding the area from here to here. As you can see, we have two congruent trapezoids. We have a trapezoid on the left and we have a trapezoid on the right. So let's find the area of one trapezoid, and then we'll multiply that by 2 to get the full area. So the area of a trapezoid is 1/2 times height times the sum of the bases b sub 1 plus b sub 2. Choosing the trapezoid here on the right hand side, the height of that trapezoid would be the distance on the x-axis that we're covering. So the height would go from 0 to 1. So the height is 1 unit. And now let's come up with the length of our two bases. The bottom base, meaning the one at x equals 0, that's 2 units tall. So that base would be 2 units plus b sub 2. This would be 1 unit tall. So the area of one trapezoid is 1/2 times 1, or 1/2 times 3. So the area of one trapezoid would be 3/2. Multiply that by 2, we know that the full area, the total area from -1 to 1 would be 3. So we would write that as the definite integral from -1 to 1 of 2 minus absolute value of x dx is equal to 3. Our definition of area required that the function that was the integrand be non-negative. For a function that is negative, when using an integral to find the area, evaluate the integral, then take its opposite. We'll keep this in mind, but first we want to look at a way to integrate a constant function. Theorem 2. Integral of a constant function. If f of x equals c, where c is a constant, on the interval, closed interval from a to b, then the definite integral from a to b of f of x dx is equal to the definite integral from a to b of c dx, which is equal to c times the quantity b minus a. Let's try this out. Evaluate the integral. We have the definite integral from 0 to 3 of -160 dt. So according to the previous theorem, this definite integral could be evaluated by taking c, the constant, which is -160, times the quantity b minus a, times the quantity upper limit of integration minus the lower limit of integration. So we simply end up with a -160 times 3, and that gives us -480. Some discontinuous functions are integrable also. Let's take a look at one. Part A, find the points of discontinuity of the integrand on the interval of integration. Part B, use area to evaluate the integral. This implying use some type of geometric formula for finding that area. The definite integral is from -1 to 2 of absolute value of x over x dx. So here's the graph of our function absolute value of x over x, and we're being asked to evaluate the definite integral from -1. So here we are at -1 over 2 positive 2. Well, at x equals 0 is a point of discontinuity. However, we can still evaluate the definite integral. We can take the area, the total area, and think of it as, well, it's the area of this rectangle plus the area of this rectangle. Let's start with the leftmost rectangle, this guy right here. You know how to find the area of a rectangle. It's base times height, or length times width. So we know that this rectangle is 1 unit in height. It's also 1 unit in length, and we multiply those two together to get 1. The area is below the x-axis, so that would be a negative area. So I'm going to write the area of the left rectangle is equal to negative 1. What about the area to the right? Area of the rightmost rectangle. It has a base of 2 units and a height of 1 unit, so that area would be positive 2. And now we can evaluate the definite integral from negative 1 to 2. It's the cumulative area from negative 1 to 2. So when we add these two together, we get positive 1. Now it's time for you to try a problem. Part A, find the points of discontinuity of the integrand on the interval of integration. And B, use area formulas to evaluate the integral. We're given the definite integral from negative 3 to 4 of x squared minus 1 over x plus 1 dx. Pause the video while you work on this problem. When you are finished, restart the video and check your solution. So here's the graph of the function x squared minus 1 over x plus 1. The graph is a straight line, however we do have a discontinuity at x equals negative 1. To find the area from negative 3 to 4, notice that we have two triangles. Let's call this triangle over here, this area A sub L for the leftmost triangle, and here we have A sub R for the rightmost triangle. So we'll find the area of each of those triangles and add them together. So the area of the triangle on the left would be 1/2 times its base. Again, I'm going to use the base being the distance from the x value of negative 3 to its corresponding y value. So how many units would that be? It has a base of 4 units. And then we look at the distance from x equals negative 3 to x equals positive 1. That could be the height of our triangle, and that is also 4 units. Now this area, A sub L, is completely below the x-axis. So we would get a negative answer. So 1/2 times 4 times 4 gives us negative 8. What about the area of the rightmost triangle? So that would equal 1/2 times its base, which again we're going to use the distance from x equals 1 to x equals 4 up to its corresponding y value. So that is a distance of 3 units, and this triangle has a base of 3 units. So the rightmost triangle has an area of 9/2. Now we need to add these together. The total amount of area, if we take negative 8, add it to 9/2, that net area would be negative 7/2. So we can write that the final answer of our definite integral, which again is negative 8 plus 9/2, is negative 7/2. In this lesson, we explored the definite integral as area under a graph. Be sure to work the exercises that your teacher assigns, and we'll see you next time.